Okay, welcome back for part two of the in-class development. This time what we're looking at is the big ideas around E and Ln as inverses. Now this is an informal way of producing this, but it's very, very valuable. So there's two ideas of what we're looking at here, and so we need to be able to discern the two ideas as we move forward. One of them, of course, is an idea related to calculus, and it's a very kind of basic non-scientific development that I'm going to do with you, and the other one is the maths idea. Now this is a very important idea because this is the one that will galvanize your thinking and help you understand that what our approach is different between when we're just dealing with the mathsy idea and when we're dealing with the calculus idea. So here again, we're going to rely on something that we've already learned about, which is y equals the y equals x. And so in this particular case, when we put y equals e to the x, anything raised to the power 0 is 1. So y equals e to the x is here. Now, what we want to recognize is when we do our y equals x line, and like this, what will happen is that we can ink up this one that we've just drawn, ink, right, making it darker, increase the page where the dots are, and then when we draw this in, what we'll get is a reflection in this line y equals x. Now, why is that significant? Because the reflections in y equals x are called inverses. The reflections in y equals x, and we can do that for any number of functions, not just this y equals x function. Reflections in y equals x are inverses. And what do we know about inverses? Inverses are characterized by this lovely word, undo. That's our go-to person, isn't it? Undo, when we're trying to make sense of that. So what's this curve? If y equals the ln of x here, if y equals e of x, what's this one? Well, this is y equals the ln of x. Wow, y equals the ln of x. So they are inverses. They undo one another. So this is a big idea. The undo of plus or minus, times, divide, a square and square root. Now we have e and ln. So let's see how that works in practice. So if we take y equals e to the x, and we say we want to solve this equation, so we want to make x the subject. So how do we get to x? Well, the first one is, your first response, I would hope, would be undo. That would, you shout that out. Undo. Okay? Now, undo means an inverse. So how do we take the inverse of e? Well, we look up here and we see that the inverse of e is ln. So we're going to take ln in this particular example. Okay? And so what you do to one side, you do to the other. So the ln of y is equal to the ln of e to the x. And look at that. Undo. Wow. Undo. And so that's just, that's equal to 1, if another interpretation. Ln of y is x. So we've solved the equation for x by using undo. Isn't that tremendous? What a terrific way to deal with e and ln, using inverses. Now, we can also do this for the other case. And I'm going to generalize it because normally we start off with general principle, but I wanted to catch your attention on e and ln specifically. Okay, so let's have a look at y equals the ln of x. How do we get to x? How do we get to x? Well, the first thing I hope that you would do is shout undo with all the enthusiasm, and then we recognize that we're going to have to take an exponential. So we're going to take an exponential, and that means applying the exponential to both sides. So we're going to raise y to the power e, and we're going to raise the ln of x to the power e, and we're going to recognize this is undo. Undo. So what we'll get is e to the y is equal to x. There it is. So we can write it in that form if it makes you feel more comfortable. So what we've been able to do is we've been able to demonstrate the solution of the equation by using undo. Now, you may not have met this before, but this recognition of E and Ln as being 1, okay, E and Ln as being 1, or the Ln of E as being 1, is probably brand new to you. So what we're trying to do is check that. So I wonder if I could just do a quick one, and if I take E and I take the Ln of E, where's my button? There you go. Cool, 1. There it is. See? And if I raise Ln to the power, now often when you use this X to the Y button, you've got to put in the bit that you want first. Okay, so we would E to the Ln, but I won't use because I'm not taking the log of anything. So I'll just leave that one. But it's the inverse; it'll give you the same thing. All right, so it'll leave you with whatever's there. It's smaller, I guess. So if I took the Ln of 2, all right, I can do it. If I took the Ln of 2 and raised it to the power of E, so if I take the Ln of 2 and raise to the power of E, Ln of 2, I want that the other way around, don't I? I want E to the power of Ln of 2. Okay, that's not what I wanted. So I want to do E to the power of Ln of 2. So when you use this thing, so I've got to do Ln of 2. So I've got to do E to the power bracket 2 Ln bracket. Should just leave me with 2. Okay. Now I could have used 1. But it's just, yeah. So just using that by hand is the easier method. I put a 2 in there, and so it was 2. Okay, I could have used 1, but I didn't want to distract from the idea that they're undo. Okay, which I think I've successfully distracted you. But anyway, we'll move on. So one of the things that happens with conventions is that we put things in conventional form. So, for example, Ln is the base log of E. It's just the form that it's been presented in. So when you see Ln with your Maths EI, okay, what you're actually seeing is log base E. So if we take y equals log base E, now I'm leading this somewhere to the x, how do I undo? I hear you saying get to x. We shout with fervour undo, and so we're going to take an exponential, and the exponential will be e to the y is equal to e to the log base e. Aha! So now there might be a more general principle that we can use. Undo is equal to 1, and so e to the y is equal to x. We've solved for x. All right. So is there a more general principle that we can use? We haven't used this before, and you've only just introduced it, so let's try it for another number. And the other number that we might consider might be y equals some other base. So what's some other base? Oops. So the first thing is we want to get to the x to solve for x. So how do we make x the subject? And I hear you say undo with fervour, because that's the standard response that we want from you. Undo, and we're going to take 7. Ooh, how's that going to work? Well, we're going to raise y, and we're going to raise log base 7. Oh, so that's a match, just like log and e was a match. 7 and log. Oh, okay. So we've got a cancellation or removal and a simplification for x. Wow. Does that work for any particular log? And what we'll see is that in fact does. Okay. So likewise, if we continue this down to its natural conclusion, what we'll see is that we get, sorry, I'm just extending this line down the middle of the page. What we'll see is that we get the same mechanism of undo in view. So in that sense, that's quite an interesting progression. So if I take y is equal to 7 to the power x, that's an exponential of the form 7, bit unfamiliar, not used to it, but you know what, that's okay. And then we've got, how do we undo? How do we get to 7? I hear you cry, undo. That's the answer, we undo. And so this time here we're going to take not the exponential 7, but a log base 7, because that's a match. Okay, so let's do that. Log base 7 for y, and log base 7 for 7, there it is, x. And this one here now is undo. Oh, gotcha. So we've found a solution for x. Wow, is it that simple? So we can do it with 10, 11, 12, whatever you like. So again, it's just that recognition, okay? It's the recognition that if you've got a base to a number, that's going to be 1, okay? If you've got a power to a base that's the same, that's going to be 1, okay? So these patterns are very straightforward. You can do it with any number, 99, 10, 0.2, 0.6, minus 7, minus 11, any pattern you like, and this undo feature will take place, okay? So this is quite a big deal in the world of doing this level of maths. So these are quite the hard ones. So that idea of undo is very much a mathy idea, isn't it? So whether we're doing 7 or 10 or 11 or the number e, which is 2.7, the irrational number, this comes into play. Reflections of the functions. Now who knew that 7, the number 7, y to the power 7, so just who knew, right? Don't know exactly what that looks like. Here we go. Y equals 7 to the x has an inverse. Oh, there's 1 again. There it is. And that is log base y equals 7. So they can be similar curves, but they're inverses in y equals x. So we can do that with sine and cos and all the other versions. So the functions themselves, if they're a function, if they qualify as a function, they'll have an inverse. So doing it algebraically as an introduction is quite hard, but doing it this way should be fairly straightforward. All right, the other thing I want to do is switch over to a calculus idea, and I'm just saying up front, I'm not doing this as a scientific development of calculus. We're not up to that in the course yet, but we've learned about linears. What's differential linear calculus all about? Well, we've got our arms waving because it's gradient. So in this case here, I'm going to use that idea of gradient and apply it in a somewhat novel way. And the novel approach is simply this. Let's have a look at our y equals the ln of x and understand what it means from a calculus point of view. Y equals the ln of x, so there it goes. Whee! Oh, a bit wonky, but that's all right. Whoops. Y equals the e of x. Jason, please. Y equals the e of x. And we'll come to a more developed idea of this in a moment. But just for now, I want to do this. Can you do this? What am I doing here? In the tutorial last week, I asked you to have a look at all of these x values and the corresponding value down on an M curve. What's the corresponding value on an M curve? If I take all those x values and project them down, and then I start plotting, what do I get? And it turns out, I should have copied this over, but I'll make it the same treacherous thing. It turns out that the M curve, or the gradient curve, is identical. So this is a huge idea, okay? A huge idea. And the idea is the M curve, or the gradient curve, okay? Now, it's the same, you say, So I'm going to call it y dash because we know that's a differential from code 1. I'm just going to use that to denote an M curve, and it's the same value. Wow. So this was developed over a long period of time. And this little idea of running gradients, little dominoes or little matchsticks or what have you, represents the curve at a point and the gradient at that point. What's the gradient at that point? So it'll be tangential. That one's not very good, so I better just draw it again. Make that a bit easier. So if we did a really big close-up and it did a micro right down deep, we get a straight bit. And that's our linear one, and that has an m equals value. Okay, that has an m equals value. And if we put together all of the m equals values for those, then what we find is that that's got to rise over the run. We find that we can denote a curve. We can plot a curve with each of those, putting them together. Okay, now we'll do that formally in a couple of weeks' time, but informally now, I just wanted to give you a sense of that. And what we can do, be a bit cheeky, it's very, very kind of rude of me to do it this way, but if I take a few other different curves just to test this idea, y equals x. Y equals x. What's the gradient of y equals x? M is 1, isn't it? Sitting in there in disguise. The gradient is 1. So if I do my little dominoes, they're all the same. So if I come up here to 1 and realise that at this x value, it's that value, I'm superimposing. Actually, I'll do it in green. I'm superimposing the M curve. I'm superimposing that. So that x value is 1, that gradient, 1, that gradient, 1, that gradient. So you get the idea, 1, and so that gradient, 1. They're all the same, all the way along. So what we get is a gradient curve, or if you like, the differential, denoted with the hat. It's the gradient curve at 1. Okay, I'm superimposing it. The gradient curve is y equals 1. So it's a very complicated idea, but but this way it's easy. This way it's a doddle, really. So what we do is we can do it for a few interesting ones. Let's have a look at we've been doing these, haven't we? Y equals x squared. We've been doing quadratics. What about if I go ahead and do little linears? Little linears everywhere, trying to represent the slope at that particular x value. And it changes to a positive, doesn't it? So y equals x squared. What does the m... And we don't know what the gradient is for that yet. We haven't even studied gradient development. But the m curve exists, and we know that there's a gradient at each point, so we're doing that here and expressing that as an m curve. What's the gradient? Okay, so what's the y dash? Now we've done this anecdotally with code 1 and code 2, and so we know that. So if we go along and pick the x value, that's a very steep negative value, so that's way down here. Okay, and it's getting less steep as each time we march along. Each one of these values we're checking. Oh, look at that one, 0. And then they start to get positive. Getting positive and positive bunched up a bit. And then as we do that, what we find is, if that's our y equals x curve, we're quite a bit steeper than y equals x. And it turns out we're twice as steep. 2x. So the M curve is 2 times as steep. So you can superimpose them and graphically do this. It's a very informal approach. It's not scientific yet, and we'll be doing the science, the mathematical sciences in the coming little while. But I wanted to show you anecdotally, if you're not sure what the gradient of a particular function is, you can just do your little matchsticks or your little dominoes, and it'll help you. Okay, so here's one that we can have a look at. Here's a sine wave. We'll use a non-scientific method to establish what the gradient might be. So this is y equals sine of x. We haven't even done this yet. But you know what we can do? We can do little linears. And the little linears are going down like this. and down like this. And so then we can plot those values at their corresponding x values. Okay, corresponding x values, we'll just plot the M curve. What does the gradient of those, each one of those little dominoes, well that's 0, isn't it? That's got a 0, so that plot there, we'll get all the 0. That one's 0, so it goes there. That one's 0, so it's crossing there. This one's 0, so it's crossing there. And then we've got these really steep ones. That's a really steep negative, that point there. So that's the biggest point of gradient. So the gradient now is the green one. This is a really big positive. So it's got its maximum gradient there. This is a really steep negative again. So if we go down and plot that. And so what we get is this picture. We get this picture of a curve. Okay, and what is this curve? Okay, so what is this curve? Well, Jason, it's the M curve. It's denoting all the little gradients at each corresponding x point. And it turns out that the hat of that is differential of sine is cos. So we'll do that anecdotally, and we'll do it scientifically. We're going to develop that when we develop calculus. But this is an intuitive way of having a look at your curves and understanding. Now, what are we doing here? We're generating curves, M curves, and so far what we've learned is, oh, wow, this is the only M curve that's the same as the original curve. Wow, so that's a big deal. That was a big discovery. So we're going back 400 years. We haven't got computers. We're using parchment or paper, ink, and maybe a feather to write with. There's no calculators, no Casios, no supercomputers, not even the computer that's took Apollo up into space. And your phone's about 10 times more powerful than that, or 100 times more powerful than that, orders of magnitude more powerful than that. They didn't even have the basic calculator. They had their brains and their minds and their ideas. So how did they develop this? How did they find the number E? So that's a really good question, because how? Why E? How did that come about? What's the process that developed that? So this is the calculus idea. So we've learned a little bit about being able to use intuitive methods to inform us somewhat, non-scientifically, but we can always check with the mathematical science. That's important that we do that. So what did they do? Well, let's try. We've seen, we've got other kinds of examples here. So let's try a few different exponential curves and see what they look like. And I'm going to wrap this video up shortly. But let's just say we superimpose some. So we've got our, y equals 3 to the x will be a little bit steeper. Still going through there. So y equals 3 to the x. Then we might change colour and go for a red one. And so this will be less steep. Still got that classic exponential shape. So y will be equal to, I don't know, let's call it somewhere between 2 and 3. Let's call it 2.5. 3 on 2, 2.5. 2 is 5 on 2. 3 on 2. Let's call it, so I want it to go between 1 or a little bit more than 1, 1.5, 2.5. Let's call it 2.5, 2.5. Okay, 2.5. And then let's do 1.5. Let's do a different colour again, maybe a purple. So that's a bit less steep. Okay, a bit less steep. And then, so y equals 1.5, say, to the power x. So what we're doing is we're looking for the M curve for each of these. So what we do is we go across and we put these little M curves on, and we do the same for the one that we did previously. 2.5, do a little M curve, and then of course we can do the one for 3 and do the M's for those little dominoes, and then we can go at every point on the x-axis and we can plot down below a version of the M curve. Okay, it's all positive. So we'll take this and we'll put it up as positive, and we'll draw it as green again. So if I do the first one, what we're going to see is that it's got a little multiplier above it, so the little multiplier is going to make it slightly steeper. So y equals 3 to the x. Nope, not the same. It does not equal y equal 3 to the x plus some multiplier. Then if we do y equals 2.5 to the x, it's also a little bit steeper. Okay, it's y equals, the derivative is 2.5 to the x times some multiplier, so it's not equal to y equals 2.5 to the x. And then we'll do the last one, which is 1.5, and what we find, of course, is that that one also is not the same. So y dash is 1.5 times some multiplier, which is not equal to y equals 2.5 to the x. So how do we find, is it possible to find one of the values somewhere in the range of 3 to 1, where we go on an explanation and we kind of find some value and plot the M curve for every single one? Now, the mathematical sciences of this is profound, and I've made the statement in the lectures that this is what separates humans from animals, in that we have these abstractions. And so there was a number that they found. And the number that they found was y equals 2.7. And it was 2.7, and it's irrational. That is, it's not terminating. It goes on and on forever, like pi, non-terminating decimal. And when it was come here, I'll exaggerate this for its importance, y equals 2.7. Wow, it's the same. And so there was this big discovery that there was a particular number, an irrational number that didn't have a pattern to it, that allowed the function to be equal to the M curve. Wow. And of course that was attributed to Euler, but there were other scientists who also contributed to this development. Wow. What a huge discovery that is. So it's the only function, y equals e, that has this property. Wow, what a tremendous discovery that is. So y equals e to the x, it's got a unique property. All of these other guys have got M curves that are very different. X squared's got 2x, sine's got cos, even y equals x has got the number 1 as its curve. It's a very unique property. It's the only function that has this property. And we love e now because of this. Because what's the differential? What's the differential of e to the x? We love it. It's itself. What's the integral of e to the x? We'll learn about these in time. We love it because it's e to the x, and there'll be some things we'll add. Wow, it's the only one that has this property, that when you apply calculus to e to the x, it remains the same function. So we can use that property to simplify our calculations. So whenever it comes up, wow, what a tremendous thing that is. Okay, so what I want to do here is just now have a look at the calculus of the ln of x. Y equals the ln of x. Okay, now y equals the ln of x, I'll just go back to being consistent with the graph. Y equals the ln of x is this guy, isn't it? We saw that it was a reflection. That's not important here. So what about if I do the little linears? I'll do our very non-scientific calculus. There we go. And plot all of those values superimposed. And this time I'll go back to green to be consistent with what I did earlier. And I'll say, what is the value? So this one here is a very steep positive. Corresponding x value, it's getting less steep. It's always positive, it's always increasing, so it's getting less and less and less. And so what we get is a curve that drops down like this. A curve that drops down like this. And so y dash, now what is this curve? it's the first quadrant of 1 over x, so it's restricted, so the domain is restricted to be x is positive, greater than 0. Wow. See, they're different. They're different functions. The ln of x is 1 over x. Got nothing to do with e. So we know that there's a link over here, a mathsy idea, between e and ln. But when we come to calculus, they're not related. So we've got to keep that clear in our minds. They're very, very different, and we don't want them to overlap in any way, shape, or form. All right, I'm going to call this video part 2, and then I'll be back for part 3.